Welcome now to session A. What is OpenFOAM? Let me start with a brief history of OpenFOAM. So the inventors of OpenFOAM are Henry Weller and Horvath Časak, at that time at Imperial College in London, UK. And the goal was to develop the best CFD code on the planet around 1996. And for you, important is that what OpenFOAM is standing for. So OpenFOAM stands for open source field operation and manipulation. So it aims at working with fields. So it was designed for continuum mechanics. Classical CFD is one part of continuum mechanics, and it's open access, open source, meaning that you can retrieve the source code of this software, compile it, modify it as you like, and give it away to others as well. So this is the whole philosophy behind OpenFOAM. An important thing for you to know is that the software design itself is rather complex. It's very layered. We have a brief look on this, and so it is really designed as a beautiful piece of engineered C++ code. And what is important to note at this point is the advantage of OpenFOAM is that it tries to mimic the equation that needs to be solved. We'll see this on the next slide. So this is typically called equation mimicking. And if we look, for example, at a specific application, we would like to solve, for example, this transport equation of a scalar quantity. In this case, is the granular temperature for a certain phase M. Then this would be the continuum mechanics formulation, this partial differential equation that needs to be solved. So we have here a time derivative, we have here a convection term, we have here a conductivity term, we have a production term, and other terms that act here as a synchro source in this transport equation. And the OpenFOAM code for this application, for this transport equation, would look like this. So on the left-hand side, we would have this time derivative. So this is in this finite volume method class. We have this functionality dtt. So this makes a time derivative of this input here. So the 1.5 is, don't be confused, this is this term here. And then we have this divergence term here. This is the divergence, a convective term. So phi data, and this is just a specification how this the term is named. And on the right hand side we have the Laplacian term. This is this term here, and then we have source and sinks. This is this tau here. This tau du is here. This term, this production term, and these are simply source and sink terms that are used in this transport equation. So this is what is called equation mimicking. So in simple words, it's pretty easy to transfer a transport equation from the field of continuous mechanics to OpenFOAM source code. What we're gonna do next, we will look into some selected slides of Professor Nilsson's slide set, and I've put them together. They are called a basic Nilsson slides.pdf, and we're gonna look at these slides in a second. Before we do this, finally I just would like to show you the copyright and disclaimer. Most important one, respect please this, and you are free to share this screencast and slides under this license, which is a Creative Commons share alike non-commercial license. Thank you, and see you soon for this PDF of Professor Nilsson.